In the last class, pre-class lecture, we started to look at reactions of alcohols. And we looked at oxidation reactions to form either carboxylic acids or ketones, and also to aldehydes with a few reagents. So now we're going to continue to look at reactions of alcohols, and what we're going to focus on today, at least to start with, is the idea of using alcohols as either nucleophiles or electrophiles, and whether alcohols can be converted to nucleophiles, and how to convert weak nucleophiles into strong ones, and then whether the OH group can be made to leave. So here's kind of a review of what we've talked about in terms of alcohols from last semester. If you had to classify an alcohol as a strong or a weak nucleophile, what would you call it? I'd call it a weak nucleophile simply because it has a neutral charge. And my definition of strong and weak nucleophiles is that a strong nucleophile has a negative charge, and a neutral nucleophile is a weak nucleophile, has a neutral and no charge. What about an alkoxide? Well, kind of gave that one away. With the negative charge, it's a strong nucleophile, but also a strong base. How do we convert alcohols to alkoxide ions? Well, it's a good question. So if I wanted to convert an alcohol to the corresponding alkoxide, go from being a weak nucleophile to a strong nucleophile, how could I do it? Well, this goes back a couple of lecture periods. I could do it by direct deprotonation. And what base would I use to completely deprotonate an alcohol? Well, I could use a C-, which comes from a Grignard. I could use NH2-, or I could use H- for the hydride. Any of those three bases are strong enough to completely deprotonate the alcohol to form the alkoxide. If you also go back a few lectures, you'll also remember that we can use sodium or potassium metal, and that will form the alkoxide and hydrogen gas, and the alkoxide could either have a sodium or potassium counterion. So these are the two ways, just to remember, how we can convert the weak nucleophile, an alcohol, to a strong nucleophile, the alkoxide. Well, we already know how to use alkoxides as bases in E2 elimination reactions. We also know that, for the most part, the smaller alkoxides, things like methoxide or even ethoxide, are most likely going to react as nucleophiles, and so we could use those to do SN2 reactions. Okay, so we can use alcohols or alkoxides as nucleophiles. Now, what about the OH group in terms of a leaving group? What kind of leaving group is just an OH? And if you said poor, you're correct. The OH actually will not leave. OH- is too strong of a base, and remember that leaving group ability is based on basicity, and it's inversely related to basicity. So hydroxide is too strong of a base for the OH to leave. We'll talk a little bit more about that as we go on here. How do I make an OH group leave? Well, I simply add acid to that alcohol, protonate it, and now all of a sudden that water could leave if this was a secondary or a tertiary carbon. If it's a primary carbon, then we either have an elimination step or an SN2 step, where a nucleophile would come in, kick off the water, or we would lose H+ and the H2O to give us the final product. So looking at this, the protonated the protonated OH group is a better leaving group. So if you go back and you remember how we did some of these reactions, for instance, we could take this alcohol, and if I wanted to react it with HCl, the first step in this mechanism would be to protonate that OH with the H+, so that it forms the oxonium ion. And in this particular case, since this is a primary carbon, the water won't leave. Instead, the chloride would come in, attack that carbon, kick off the water molecule to then give me a substitution product. We also did dehydration reactions. If you remember, we took an alcohol and we treated it with either H2SO4 or H3PO4 and heat, and that would protonate the OH. The water would leave, we'd get a carbocation, and then we would get the formation of the double bond. So in this case, we would make this as our product, and remember that this always gives the Zaitsev product, which is the most substituted product. So this is just a couple of reactions where we force the OH group to become a leaving group. Now, we are going to want to have OH as a leaving group, but how do we do it if I'm reacting, for instance, an anion? So let's say that I gave you this reaction and I said, let's take this alkynyl anion and let's react it with, and I'm going to change these R groups so that we'll make this a real problem. Let's make this a methyl group, and let's make this, let's make that. So if I gave you this problem and said, what's the product of this reaction? Oops, sorry. If I gave you this problem and said, what's the product of this reaction, what would you write? Amuse me and take a minute and write down what you think the product of that reaction is. Now, those of you who looked up here and said, oh, well, I'll write that product, wrong. This is a strong base, and what would it do? It would deprotonate that alcohol. So instead of doing perhaps an SN2 reaction, I would take the proton off of the alcohol, and I would make the alkoxide. So these would be the products of that reaction. So how do we, in essence, substitute for an OH when I have a nucleophile that is negatively charged and very strong? And I'll give you another example here of a question that I will sometimes ask when I start out this topic. I'll say, okay, react this with NH2- and tell me what the product is. And then, just to sort of be more misleading, I'll say, but now let's go ahead and let's use potassium tertiary. So what would be the products of these two reactions? And a good portion of the time, I'll get people to form a double bond between, let's say, these two carbons, or I'll get people to write a double bond over here, when in fact neither one of these reactions occurs. This NH2- is a stronger base, and so it'll deprotonate that OH group to form the alkoxide, and we would get NH3. and over here the tertiary butoxide, and I probably would write equilibrium arrows here, and I would again get an alkoxide, or I'd get that alkoxide plus tertiary butyl alcohol. Now this would be an equilibrium because these are two alkoxides. The N- is a much stronger base and would completely deprotonate the alkoxide. But either way, you can't eliminate an OH group using our strong base. Remember, what compound did I have to use in order to get this reaction to occur? It wasn't an OH group, it was a halogen. And that halogen I could have reacted with NH2-. So if X was Br or Cl, then I could use NH2-, then I could use the tertiary butoxide ion. And if I use the NH2-, I would get the more substituted, sorry, that's not the more substituted product. I would get the more substituted double bond. If I use the tertiary butoxide, I would get the least substituted product. The so-called Zaitsev product for more substituted, the so-called Hofmann product for the least substituted. So when you're doing eliminations, we have control over forming the double bond in the most substituted position or least substituted position, but we can't do that if we start with alcohols. If we start with an alcohol, how would we form, let's see if I got another slide here, nope. I'll go ahead. If I had this alcohol and I said I want to form the two double bonds, that one, and let's say I wanted to form the least substituted double bond, I could definitely form this one by using H2SO4 or H3PO4 and heat. But remember that this goes by Zaitsev's rule to give you always the more substituted double bond. So down here, how can I form this product? And that's where people will oftentimes come back and suggest, well, we'll just use the tertiary butoxide ion, and that'll give us the least that'll give us the least substituted double bond, when in fact it'll simply deprotonate. So the idea here is that we can do lots of eliminations with strong bases or strong nucleophiles and alkyl halides, but when an alcohol is involved, we cannot simply react that with a strong nucleophile or a strong base, because it will deprotonate and it won't do substitution or elimination. So how do I change the OH group then from being a poor leaving group to something that will leave? And you might say, well, wait, you just said that in one of the last slides. Let's go ahead and let's take and simply protonate that OH group. So if I wanted, let's say I took this alcohol and I went ahead and added H plus to it, and I form my oxonium ion, you might say, okay, well, great, and now you could go ahead and maybe you could react that with this alkynyl anion, and it'll come in and will displace off the water group. Well, what would the product of this reaction be? Well, it's not going to be a substitution reaction. It's going to be another acid-base reaction. This C- is just simply going to come in and pull off that proton so that we would just basically form the alcohol, and we would protonate what was our alkynyl anion. So we can't protonate OH in the presence of an anion, because the H plus will go straight to the anion and it won't be a nucleophile anymore. So again, how do we make the OH a good leaving group? Well, we need some new methods. And one of the new methods is to take and convert that OH group into what's called a sulfonyl ester, or a sulfonyl ester. And I'll give you a specific one, which is called the tosyl ester. And that's using this molecule. So what we can do is, if I want to convert the OH group into a good leaving group that will be compatible with strong nucleophiles like Grignards, alkynyl anions, even H-, what I do is I react the alcohol with a sulfonyl chloride. And in this reaction, HCl is lost, and the oxygen forms a bond to the S double bond O groups. And then there's over here, there's an alkyl group, which most often is this benzene ring with a CH3 group on it. But if we convert now this OH into this ester group, this sulfonyl ester, this will now become a really good leaving group. And in that case, what will happen is that if we have that sulfonyl ester, we can then have the nucleophile come in and attack this should be the carbon of that R group, and that nucleophile will attack this carbon and kick off this entire sulfonyl ester, and it will leave, and it is an excellent leaving group. So in essence, what I've done is I've converted my OH into a group that can be substituted for by a negatively charged nucleophile. There's no question about whether this group will leave. It definitely will. And there's no deprotonation possibility, so I could react this with Grignards, alkynyl anions, really strong bases, but the strong nucleophiles as well. Now you might say, okay, can you do an example of this? And let me go ahead here and do an example of what I'm talking about here. Let's say that I wanted to convert propyl alcohol into add a benzene ring to it. Let's see if I can draw my benzene ring properly. Well, we can't do this reaction by reacting that alcohol with this Grignard. Right? If we think we're going to do SN2 on this, we couldn't do this because the Grignard would come in and deprotonate that OH and wouldn't substitute for it. We can't add acid to this to protonate that OH group, because when we added acid, it would protonate the benzene ring and the Grignard would be lost and no longer a nucleophile. So what we instead would say is, okay, if I want to do this reaction, let's go ahead and take this alcohol and react it with this particular sulfonyl chloride. And this is called tosyl chloride. by a mechanism that I'm not going to talk about, we would lose HCl in this reaction, and I would then form this tosyl ester. Then I could take that tosyl ester and I could say, okay, now let's go ahead and use my Grignard as a strong nucleophile to come in and attack that carbon. And then what would happen is this entire group would leave, so that I would form I would add my benzene ring onto my propyl chain, and I would get that as my leaving group. And there's other variations on this. Once we convert the, I'll show you, once we convert the OH to the tosyl ester, we could think about doing eliminations by E2 by using NH2- or tertiary butoxide, because again, this tosyl ester isn't going to be deprotonated. It's just simply going to be a really, really good leaving group. So in this case, I'm doing that reaction by an SN2 mechanism. I'll talk about E2 in a couple of minutes. So formation of tosyl esters allows us to convert the OH, which won't leave, into a leaving group that is compatible with really strong negatively charged nucleophiles. Okay. Now, why is the tosylate, or why is this tosylate a very good leaving group? To understand that, we need to go back to this. We can go back to this slide. So why is this a good leaving group? Well, remember what makes a good leaving group. Leaving group ability is going to be inversely related to basicity. So I want my best leaving groups are going to be really weak bases. You come down here and say, well, why is this a really weak base? Well, you might say because its conjugate acid is very strong. So this is a very strong acid, and this correspondingly would be a very weak base. So let's write that equilibrium out. I would get H+, and then I would get the conjugate base, which is in this case the tosylate part. Why is this a weak base? Because this is a very strong acid. Why is this a very strong acid? Because it dissociates very highly. Why? Remember, we talk about the equilibrium being pushed to the right when the conjugate base is very stable. When you have a very stable conjugate base that pushes the equilibrium to the right, we get dissociation and more H+, hence this acid becomes very strong. And since the equilibrium is pushed to the right, the sulfonate here does not abstract hydrogens very well. So therefore, it's a very weak base. Why is this very stable? Resonance. Okay. So tosylate make very good leaving groups because they form lots of resonance structures, therefore are very stable, and therefore are very weak bases, which makes them excellent nucleophiles. Or excellent leaving groups. Okay. So convert the OH group to the tosylate, and once you convert it to the tosylate, then you can go ahead and do these SN2 mechanisms. You could do E2 eliminations if you wanted to by simply reacting it with a base, be it an NH2 minus or a terse butoxide. Do I have an example of that? Well, how about, where was it? This example. How could I take this alcohol and convert it to the least substituted double bond? I know how to make the most substituted double bond. Just simply do dehydration, and that favors the Sadzev product. How would I accomplish this reaction? Well, then I have to go to another blank slide here and say, okay, if you want to do that reaction, what I'm going to do is I'm going to take my alcohol and I'm going to add it to my tosyl chloride. I'm going to lose HCl out of this process. So I'm going to form this tosylate ester. Oops, forgot my methyl group there. So now this leaving group is now compatible with strong bases. They won't deprotonate it. So now I can say, okay, I've got two possible hydrogens that could be removed by a strong base. If I want to remove hydrogen A here, what should I use? I should use terse butoxide. The terse butoxide would come in, deprotonate HA, pair of electrons would move there, and then the tosylate would leave, so that it would be very easy for me to form then the double bond over there. You could say, well, couldn't you use the NH2 minus to deprotonate HB? And sure, you could use that. Then this pair of electrons would move there. So you could form from that tosylate, you could form the more substituted double bond. Now, why you would want to do that when you could simply treat the alcohol with sulfuric acid and heat and get the same product, this would be an extra couple of steps. You're probably not likely to do that. But if you want to form the least substituted double bond, then you have no choice but to convert the OH to tosylate. Then you can do your E2 reaction. Okay, so if we want to make OH groups good leaving groups that will leave and that will be able to form double bonds or do substitutions, and leaving groups that are compatible with strong nucleophiles that are also strong bases that are negatively charged, you have to convert the OH into a tosylate. Okay, so that's the use of tosyl esters. How about some other reactions of alcohols? Well, one of the next reactions we can look at is how do you eliminate an OH group altogether from a molecule? We could say, oh, well, I don't know how to do that. Because if we thought about potentially taking H minus and having H minus come in and kick off the OH group, well, we have all sorts of problems there because number one, the OH group doesn't leave, and number two, the H- would simply deprotonate the OH. Well, there is a two-step workaround for that. If you wanted to remove an OH from a molecule, how about we protonate it and use heat? So in other words, this is the dehydration part. Do a dehydration reaction to get a double bond, and then use hydrogen and platinum or palladium, and you would go ahead and reduce that double bond down to a single bond, and the net result is that I've replaced an OH with an H. I've reduced the alcohol. But now we know about the tosyl chloride, so we could say, hey, I like this idea of H-, so let's take the alcohol and react it with the tosyl chloride. And when I do, I make this tosylate ester. And now let's use H- as a strong nucleophile so that it comes in and kicks off the tosylate. And if it does that, then we could do an SN2 reaction to give us our reduced alcohol and replace an OH group with an H. Okay, so you could either of these are a two-step process. There's no one-step process to get rid of an OH group. But this is how we could reduce alcohols. A couple of ways. Now, how about some more reactions of alcohols? Well, last semester we saw that if you take an alcohol and you react it with HX, where HX is HCl, HBr, or HI, that we would substitute the OH for the halogen. The mechanism depends on whether it's a primary, secondary, or tertiary alcohol. So if you got a tertiary or secondary alcohol, you would add your H plus and then let's say your Cl minus. The H plus would protonate the OH. If this is secondary or tertiary position, the water leaves, giving you a carbocation. Then the halogen comes in and adds so that you get your final product, and I've substituted for an OH a halogen. Now for primary alcohols, the mechanism isn't SN1 because this is a carbocation based mechanism, it's SN2. So again, if we were to add an alcohol to an acid, we would first protonate the OH group to form the oxonium ion. And then if we did that, our halogen then could come in and attack the carbon with the oxonium ion. So the X- in this case, the Cl or the Br, would come in and kick off that water. Now the actual transition state structure for that would look like this. Where I'd have a delta minus charge on the chlorine and a delta plus charge on the oxonium ion. So they would go through this SN2 transition state to get to the final product. And then over here I would also have water as the final product. So we can replace or substitute an OH with a Cl or with a Br using HX. It'll occur by either an SN1 or an SN2 mechanism depending on the type of alcohol you have. This actually is the basis, and I digress here for a moment. This is the basis for another qualitative analysis test that actually goes with the chromic acid test that I talked about in the last lecture. Remember, in the last lecture we were taking alcohols, and depending on whether the alcohol was primary, secondary, or tertiary, when you reacted this with CrO3 and H2SO4, the chromium 6 in this case was orange. And so if we saw the disappearance of the orange color, we knew that the alcohol was either primary or secondary because it was being oxidized to a carboxylic acid or a ketone respectively. If the solution stayed green, then that means I'm sorry, what am I thinking? I did this backwards. If it's green, if the solution turned green, then you get then it was a primary or secondary alcohol. If the solution stayed orange, then it turned out to be a tertiary alcohol. The primary secondary alcohols are oxidized, and the chromium 6 becomes chromium 3, which is green in color. If it's a tertiary alcohol, it can't be oxidized, and so that chromium remains orange. Well, how do you differentiate then between a primary and a secondary alcohol? You can't do it by the chromic acid test, but the Lucas test actually turned out to be a very good one for this. And so what would happen is that the Lucas test, you take your alcohol and you add HCl to the alcohol with either zinc chloride. Now, zinc chloride is usually added as a catalyst. And if this reaction can occur, you form the alkyl halide. Now, if you were in lab last semester or in the previous spring, when we did SN1, we did the SN2 reaction of butyl bromide to make butyl bromide. And so we reacted butyl alcohol, which is a primary alcohol, with sulfuric acid and sodium bromide. What had to happen for that reaction to occur is the OH was protonated, and then the bromine would come in and do an SN2 reaction to make the alkyl halide. And so one of the things that this test relies upon is the fact that the alkyl halide is insoluble in the alcohol water solution or alcohol acid solution, and therefore you get two layers. So if you form an alkyl halide, this then forms a second layer. And if you remember in our SN2 reaction, we saw the formation of a various colored top layer. Well, we had to reflux that reaction for 45 minutes. We're going to do this reaction at room temperature. So the only way that you're going to get a second layer is if this alcohol can form a carbocation. And then you'll see the layer depending on how quickly the alcohol can form a carbocation. So if we take a primary alcohol and react it with HCl and zinc chloride at room temperature, we're not going to see any reaction. We have to heat this solution up in order to get the S2 reaction to occur. If we take a tertiary alcohol and we react it with HCl, what's going to happen is that's going to go through the tertiary carbocation, and that's going to be very quickly, that carbocation is going to be formed, and so the alkyl halide is going to be formed very quickly. So we're going to see the immediate formation of a second insoluble layer. That's if we have a tertiary alcohol or any other alcohol that can form a carbocation very quickly. How about secondaries? Well, secondaries can form carbocations, it's just going to take a while. So typically with a secondary alcohol, if you see a second layer form within about 10 minutes, we conclude that yes, that is a secondary alcohol. So these two results from the Lucas test, which is alcohol plus HCl and zinc chloride, these two primary and secondary alcohols can be very easily differentiated from each other in that reaction. We also can confirm that we have a tertiary alcohol because if the chromic acid doesn't oxidize and turn green, then we should see the formation very quickly of a second layer. So the Lucas acid, or the Lucas test, and the chromic acid test actually go together, and they provide complementary information about whether an alcohol is primary, secondary, or tertiary. Okay. But now let's go back to this idea of reacting an alcohol with HX and substituting a halogen for the OH. There are some issues with it. Number one, despite the fact that I wrote HI before, HI really doesn't react. Primary and secondary alcohols require heat for them to go at a relatively reasonable rate. That's what we saw last semester in lab when we had to take our alcohol and, in essence, our sulfuric and sodium bromide solution, which was HBr, in essence, that mimicked that. We had to heat it for 45 minutes in order for the reaction to go. HX can also lead to elimination when you heat it. So in other words, if I form an oxonium ion and I need to heat, as in the case of a primary and secondary alcohol, there's nothing really stopping me from losing this H plus and doing, in essence, E2. So we're going to have the formation of some elimination product, and that's going to cut down on our yield. And then the last limitation of adding HX to an alcohol to do substitution is the idea of carbocation rearrangements. I talked about carbocation rearrangements last semester. For instance, here's an example of a carbocation rearrangement that occurs if I was to try and replace this OH with a Br using HBr. I would not get the product that I desire. Instead, what would happen is my OH group would be protonated by the H plus, and I would end up forming at least initially that oxonium ion. Now the problem here is that this tertiary butoxide, this is actually a tertiary butyl group, is going to block the nucleophile from coming in and kicking off the water. So what's going to happen is we're going to have the methyl group shift over to the CH2 position and then have the water be lost, so that I end up with a 1,2 methyl shift occurring that would then give me a tertiary carbocation, and then that tertiary carbocation, the Br minus, will now come in and add to that tertiary carbocation and make that final product. So that's one example of a methyl shift occurring to give the more stable carbocation. And remember, the driving force for these rearrangements is the formation of a more stable carbocation. Here's another example of a rearrangement where if I tried to replace this OH group with a Br using HBr, that wouldn't happen. Instead, if I was to protonate the OH, I would end up forming this oxonium ion. Now in this case, this oxonium ion, the carbon oxygen bond could break. I could lose water here to then form that secondary carbocation, which is stable. But the molecule looks and says, you know, if I shift this hydrogen over here and I do a 1,2 hydride shift, I'm going to end up forming a more stable tertiary carbocation. And then that more stable tertiary carbocation is what the Br minus is going to add to, so it's going to come in and add here. So I'm not going to get the product where I've directly substituted the Br for the OH. Instead, I'm going to get a rearranged product, which I didn't want. So there's a number of limitations on adding HX to alcohols and converting them to alkyl halides. Now, an alternative to doing HX addition that avoids most of those issues is to use another reagent that will substitute a halogen for an OH. There's many of these available, but we'll just talk about a couple of these. If you want to replace the OH with a chlorine, you can either use phosphorus trichloride or phosphorus pentachloride, and that will substitute OH for Cl. The mechanism for this, you can look in your book and they'll kind of give you some sort of hand-waving arguments that aren't particularly useful. So we're not going to talk about the mechanism of this reaction. You just have to remember this is what PCl5, PCl3 do. Their only job is to convert OHs to Cls. If you want to do bromine, if you want to replace an OH with a bromine, you can use PBr3, and that will also substitute a Br for an OH. Now the advantages that these reagents have are that they react very easily with primary and secondary alcohols. So there's no need for a lot of reflux if you're using these reagents. So last semester we could have saved ourselves 45 minutes had we have not reacted the butyl alcohol with HP or with sulfuric acid and sodium bromide if we instead added just PBr3. And the other thing that these reagents do is they replace the OH even if there's a possibility for rearrangement. So no rearrangements occur because these reagents don't go through an oxonium ion intermediate. So these are actually a preferred method of converting OH to an alkyl halide. There's another reagent that you can use to convert the OH to the Cl, and that's to use what's called thionyl chloride, SOCl2. And here's its Lewis dot structure. So when you react an alcohol with SOCl2, you'll replace the OH group with the Cl, and then you'll get a number of byproducts, HCl, sulfur dioxide. And so this is basically the equivalent of your PCl3 or PCl5. But there is something special that occurs with thionyl chloride, and that is that if we were to use an optically active alcohol, there's actually three possibilities that we could have stereochemically for substituting a halogen for the OH. One is we could get retention. The chlorine goes in exactly the same position as the OH started in, 100%. We could get 100% inversion. We could probably get somewhere in between 100% retention and 100% inversion, and that would depend on the particular reaction. Or we could get a racemic mixture out if we go through a carbocation intermediate. So the first thing we'll talk about is what does SOCl2 do, and it turns out that it reacts and it gives retention of configuration. So if I had, for instance, this is S2-butanol, or S-butane 2-all, if I wanted that S to stay S in the final product, I would use SOCl2. What would happen if I reacted a chiral alcohol with HCl? Could you work out the mechanism for this and tell me what happens to the stereochemistry of the product? Do I get retention? Do I get inversion? Or do I get a racemic mixture? And if you're an overambitious go-getter student, you might want to stop the tape and see if you can write this mechanism out, including the stereochemistry. And hopefully you tried to write that mechanism out. If you didn't, then you're apparently not an overachieving go-getter student. So let's take the OH, and the first step is going to be to protonate the alcohol. Nothing exciting there. Forms an oxonium ion. The only thing that's tedious about this is keeping the stereochemistry in the product. What's going to happen next? If you said the carbon-oxygen bond would break and we would lose H2O, you were right. And so now what's going to happen? Now what's going to happen is I'm going to form this carbocation. What's the structure of that carbocation? Well, it's sp2, and it has, let me just switch this up. It's got an empty p orbital. It's like deja vu from first semester. Well, once I protonate the OH, it becomes a oxonium ion, and then the water leaves, and I form a carbocation. What happens to the stereochemistry of the molecule? Well, the Cl- could come in and attack here, or the Cl- could attack this lobe. It's going to do this 50% of the time. It's going to do the other 50% of the time. And so therefore, I'm going to get a mixture of retention namely the S. If, let's see, this one started out to be S, and I'm also going to get okay, so then I'm going to get the R. So I'm going to get a 50-50 mixture of these, and that's going to be a racemic mixture. Okay. So if you want to make a racemic mixture, great. React the secondary or tertiary alcohol with H plus Cl minus. That'll give you a racemic mixture. Of course, then you could say, what if I want to do inversion? If I want to do inversion, what am I going to do? Well, somewhere I have to have an inversion step. So how about we do this? Let's take our alcohol and react it with our new friend, the tosyl chloride, to make a tosylate ester. And since that's now a good leaving group, let's take a chloride, dump it in there. The chloride would come in, kick off the tosylate ester, and guess what happens? What happens is that we end up with now inversion of configuration, because this is an SN2 mechanism. So I'm going to end up with a product that I suppose looks like this. Right? If this one started out S, then this one is going to start out, that final product is going to be R. So we can use the tosylate ester and the fact that we're going to do SN2 to do inversion 100%. So you can convert alcohols, chiral alcohols, to either R, or to do inversion, to do retention, or to make racemic mixtures, depending upon what set of conditions you use. Okay. Right. So that's the lecture for today. If we go through a quick summary, the quick summary of what reactions we looked at was, we started with the idea of how we can convert a weak OH nucleophile into a strong one by simply deprotonating it and turning it into an alkoxide. We can turn an OH group from being a poor leaving group into being a good one by the method that we used last year, simply protonating it. But that's not going to work if I'm going to try and substitute the OH group with a strong base that has a negative charge. And so in that case, I'm going to have to convert my alcohol into a sulfonyl ester or a tosyl ester, more specifically, and then I can do SN1 or SN2 and E2 reactions on that what was an alcohol, which is now the ester, since now that's a really great leaving group. We can completely replace an OH group with a hydrogen by two methods, either dehydrate the alcohol to form an alkene and then do hydrogenation on it, or use the tosyl chloride and convert the alcohol to a tosyl chloride, and then use hydride to do an SN2 reaction and displace the tosylate ester or the tosyl group to then replace the OH group with a hydrogen. HX addition we talked about last semester. It works. It has its limitations, and in order to overcome those limitations, what we really need to do is to use either PCl3, PCl5, PBr3, or SOCl2. We can sort of extend that to do either an inversion, a retention, or racemize the center, depending upon which one of those reagents that we use. And then finally, we have to remember that we can get carbocation rearrangements with alcohols plus HX, and that's one of the limitations of that substitution of an OH group using that acid. Okay, so there will be a online quiz for this, and if you have any questions about these reactions, we will do some problems, write products, try and figure out how to do reactions of chiral alcohols, which reagent should I use. We will do all of that in the lecture period for this class lecture.